For this video, I'm going to jump right into a bit of code to demonstrate one more factory method on the executors class. I've created a new project called Parallel Processes with the main class and main method. I'll set up a variable to set the numbers to be processed, so in this case I plan to process 100,000 numbers. I'll generate an array of randomly generated longs using the numbers length to limit the array to 100,000, as well as limit the numbers to be between 1 and 100,000. I'll quickly use a stream to give me the sum of those 100,000 numbers. I can get a stream from the arrays class's stream method, passing it my array of numbers, and just call the terminal operation sum there. I want the result to be a long. I'll print that out. Running this code, I'll get a value that will be different each time I run it because of the random values used. I included this here because I want to verify the sum I'll get after I split up this summation operation into multiple subtasks. Now, you'll agree, whether some of these numbers in a single array of 100,000 records or in 10 arrays of 10,000 records and summing those 10 results, the final sum should be the same. Splitting the summation task into tasks operating on smaller sets of data and performing them in parallel might not be the best case scenario for parallel processing, but it's an easy one to understand, I think, as we look at this next type of executor service. This is the work stealing thread pool. I'll create a work stealing pool. Again, I just use the executors class factory method to do this. The number I'm passing to this pool is not technically the number of threads that will be executed. It's the level of parallelism I want, and you'd usually set this to the number of CPUs available on your system, or less. So what's a work stealing pool? The work stealing thread pool is used for parallelism and concurrent execution of tasks. Each worker thread has its own task queue. When a worker thread finishes its own tasks and its queue is empty, it can steal tasks from the back of other worker threads' queues. This helps to balance the workload among threads, reduces idle time, and optimizes resource usage. In the case of my code here, I'm going to demonstrate how you might split up the single task of adding 100,000 numbers into smaller tasks. I'll use my work stealing pool to distribute the work. I'll first set up a list of callable tasks, each will return a long value. I use the long wrapper type since we can't use primitives with generics, and I'll just instantiate that as a new array list. I'll create 10 subtasks. Each subtask will sum a tenth of the randomized array. I'll set up a variable for the number of tasks and set it to 10. Each array will be the total number of elements divided by the task number, so in this case it will be 10,000. I'll loop from 1 to 10. I'll get the starting index, which is I, times the element count each task will process, so split count. I'll get the ending index, which is just the starting index plus the split count. I'll add a callable lambda to my tasks array list. In the lambda, I'll sum up the numbers the old-fashioned way with a simple for loop and use the addition operator to keep the running sum. I'll return that sum from the task so the calling code can get it. And that's that for the creation of these 10 tasks. I'll submit the tasks to the thread pool and wait for all of them to complete. I want a new sum variable, and I'll loop through the future results, adding each future result to the task sum variable. Finally, I'll print the sum of the tasks out. And I can't forget to shut down the thread pool. I'm getting an error from the invoke all and get methods, so I'll add a throws exception to the main method. If I run this, I'll get the same sum as I did when using a stream, so that's good. I'll add one statement to this code to print out the actual class name of this work stealing pool. I can include this after the shutdown, so I'll print the full class name of this pool's instance. Running this now. I see that the thread pool is really something called a fork join pool. The fork join pool class is Java's implementation of the work stealing pool. It's based on the fork join or divide and conquer algorithm of computing. This algorithm breaks down a complex task into smaller subtasks, processes them independently and in parallel, and then combines the results to solve the original problem. I'll bring up the API documentation for this class just to show you a couple of interesting points about it. The first thing we're told is that it's an executor service for running fork join tasks. Now, my code never did anything with a fork join task. But if I continue reading, I can see that it's also an entry point for submissions from non-fork join task clients, which is the way I just executed it. It then tells me this pool is different from others because it steals work, which I've discussed already. This means a thread in this pool won't sit idle if another thread has work in its task queue that this thread can do instead. More interestingly, I want you to focus on this statement. A static common pool is available and appropriate for most applications. And then, using the common pool normally reduces resource usage because its threads are slowly reclaimed during periods of non-use, so it's recommended to use this common pool in many circumstances. It's actually the pool that's used when we use parallel streams, which I'll be talking about next. Before we go back to the code, first I want to look at the methods available on this class. There's some interesting ones here, and I want to encourage you to explore learning about some of these on your own. I'll scroll down to the submit methods and show you the several overloaded versions listed here. Notice we've got submit methods that takes a runnable and a callable, and there's a different one for this class that takes a fork join task. I'll click on that class. A fork join task is an abstract base class. It's thread-like but much lighter weight. Then we're told huge numbers of tasks and subtasks may be hosted by a small number of actual threads in a fork join pool. That sounds promising. Notice the three direct known subclasses: a counted completer, a recursive action, and a recursive task. Let's get back to the code and look at the fork join pool's common pool. I'm going to change the type of my thread pool variable type to be a fork join pool. I need to cast the result of the new work stealing pool to a fork join pool as well. I'm doing this because I want to use a couple of the methods that are specific to this class. I'll start by printing out some information after I've invoked my tasks. I can print the level of parallelism. I can print the pool size. And I'll print the steal count. I'll run this. You can see that the parallelism is 4, which matches what I set up, and the pool size is the same. The steal count is the same as the number of tasks I submitted. If I rerun this a couple of times, I always get the same results. Now, I'll switch to the common pool. I'll remove everything to the right of the equals sign and replace it with forkjoinpool.commonpool. I don't need to cast the result of that because it returns a fork join tool type. If I run this code, it works just the same as before. Notice now that the numbers are different. The parallelism for my system is 15. The pool size is 3 when these statements were executed, and the steal count is only 4 or 5. I'll run this a couple of times, and you'll see the pool size and steal count may change by 1 or 2 each time. I can get the number of CPUs on my system, and I'll do that now. I haven't really talked about the runtime class, but it can give us information about the running system, including the number of available processors. I'll rerun this, and I can see that my system has 16 CPUs. In general, the common pool will use as many CPUs as possible, but won't typically use all of them, and we see that here with 15 as the parallelism count. The common pool starts with a small number of threads in its pool, and it will add more threads as needed. Threads will also be removed if they're idle for too long. The steal count returns an estimate of the total number of completed tasks that were executed by a thread other than their submitter. When parallelism is higher, there's less work stealing. Next, I want to show you how to use a recursive task. I'll set up a class in my main Java source file that extends the recursive task. Recursive task is generic and I wanted to return along the sum of all my numbers in my array. This code doesn't compile because I have to override the compute method, so I use IntelliJ to help me do that. Before I code this method, I'll add a couple of fields. I'll set up an array of numbers. I'll make this an array of long so it matches what I had previously. I'll include a field for a starting index and a field for an ending index. Lastly, I want to divide up the tasks, so if I pass 2, it will create 2 tasks. If I pass 4, it will create 4 tasks, and so on. I'll generate a constructor. Now, it's time to talk about the compute method. I'll first remove the default statement, return null. If the end index minus the start index is less than the array length divided by the number of tasks, that means the array length is smaller than the size we want to split by, so it will process it here. I'll print the start and end index. I'll initialize a long sum variable. I'll loop through the numbers array, starting with the start index up to the end index. I'll add each number to the sum, and I'll return the sum. If we weren't dividing the array up, or if I pass 1 as the value for division, this would be the only code I'd need. But I want to split up the work, so I'll include an else statement. I'll first get the midpoint between the start and end index. I'll create a recursive task for the first part of the elements, which I'll call left task. I'll create a second recursive task using the second half of the elements. The fork method will execute this task in the same pool the current task is running in, so I'll kick off the left task and I'll do the same for the right task. Finally, I can call join on each of those tasks. The join method here on recursive task is similar to calling get on a future instance. It returns the result of the task as computation when it's done. It doesn't, however, throw a checked exception. In this case, I'll add the result of these 2 tasks. This method will continue to spawn 2 recursive tasks until the size of the elements is within the range for each division. Now, let's actually run this. I'll insert code before the call to the shutdown method on the thread pool. I'll create a new recursive task variable called task and instantiate a new task. I'll pass it my numbers array, the starting index, 0, and the ending index, the full size of the array, and I'll pass 2, that's the division, or the number of tasks I want this to run in. I'll get the sum, calling the variable fork join sum, and assign that what I get back from calling the invoke method on thread pool, passing it my recursive task. Then I'll print that sum out. If I run this, you'll see the results of the previous code, but then you'll see that my recursive task split the array up into 2 tasks as I requested. And I get the same result, the same sum of numbers for all 3 methods, so that's good. I'll dial that number up from 2 to 4 and run it again. Now you can see that the array was split 4 ways with the same result as the other methods. I'll change it to 8 next and run it again. Now you can see that each task is processing 12,500 records. Okay, so I hope this helped you see how the tasks are recursively split into smaller tasks. The fork join pool uses parallelism to divide up the work. There are 2 main types of parallelism. Task parallelism divides a program into smaller tasks that get executed concurrently. Each task can run on a separate thread or processor core. Data parallelism processes different parts of the same data concurrently. In the example I've shown here, I've really been doing data parallelism. It's more common for data parallelism to take advantage of parallel streams. I'll be talking about parallel streams in the next video, so I'll see you there.